So last time we had left off inside of section 5.2, we had been talking about the definite integral. There's still a little bit of example and foundational stuff we need to kind of talk about. So we'll finish up 5.2 today and then kind of see where we're at in terms of whether to start something else new or not. Probably not, as there's still quite a bit left to do in this section. So our next example here says set up an expression for the integral from 1 to 3 of e to the x dx as a limit of sums. And then part B says use a computer algebra system to evaluate this expression. So if you have like the CAS calculator like Jackson or who else has one in here? Tegan, you got one too? You could type this in and just have it spit it out. We're going to do it by hand because we have all the tools we need to do it by hand. And quite frankly, I scoff at your computer algebra system. But yeah, so that's going to be this. So here we start by our setup. So we know from definition 2, that this integral is the same as the limit as n approaches infinity, the sum from I to n of f of xi delta x. So first things first, I need to come up with my value for delta x. So again, that's b minus a over n. And I need to come up with an expression for xi. In our definition for the definite integral, we just have this set using right endpoints. So if that's the case, this is going to be a plus I times delta x, which just turns into 1 plus 2i over n. So we can write this then as the limit, n goes to infinity, the sum, I equals 1 to n. So f of x is e to the x. So we have e to the 1 plus 2i over n because we have f of xi. Everybody's okay with that? Where our f is e to the x, we're plugging our xi in for that. And then we have times our delta x. So that's our limit of sums, right? Everybody's okay there? Now, part B asks us then to evaluate that expression. So first thing I'm going to do is I'm going to observe that this doesn't depend on I at all. So it's independent of the sum. So I can pull that piece out front of the sum, but it still depends on n. So it needs to still stay inside the limit. Now, the sum that I have, the sum from 1 to n of e to the 1 plus 2i over n, I recognize as a finite geometric series. So I remember from my Algebra 2 class, that this is I can evaluate the finite geometric series using that formula. The problem with where I'm at is my expression here doesn't match the form that I need in order to use this formula. So I'm going to have to do a little bit of algebra rearranging to get that to match so I can just plug it into the formula. Everybody's cool with that plan? So as a little aside then, I'm just going to take that e to the 1 plus 2I over n, and I'm going to try to rewrite this so that it matches that form there. Everybody's okay with that? Okay. So I'm going to get rid of the 1 plus that's inside the exponent. I remember when I multiply two numbers with the same base, I add their exponents. So I can rewrite this as e to the first times e to the 2I over n. That gets the 1 out of the exponent for me. Everybody's okay with that? And then I'm going to think about e to the 2n times I, like that. Because I remember when I have a product in the exponent, that's the same thing as the exponent of an exponent. Everybody's good with that? So now I have like an r to the I. I've rearranged it so I have like an r to the I. So I just need to get that minus 1 up there. So the easiest way to do that is just to put a plus 1 and a minus 1 on it. Everybody's good with that? And with the plus 1, I can do the same trick that I did before. So I can take an e to the 2 over n to the first. And this is now going to be what I want. So I'm going to go back to that expression that I was working on earlier. And I'm going to replace my e to the 1 plus 2I over n with this expression. But notice that that expression doesn't, oops, we're down here, sorry. That this expression, this piece doesn't depend on I, this piece doesn't depend on I. So both of those I'm going to actually suck out front of the sum. Does that feel okay with what I did there? And now if I look, this matches the form that I need there. So I'm going to go ahead and plug into my formula. My a sub 1, in this case, is just going to be 1. Right, because there's no coefficient in front of that, which is fine. So I'm not going to bother with writing that. And my r is e to the 2 over n. Is that okay? Yes. Yep. Again, I'm just using this formula down here to come up with that. Oh no. Okay. So 1 minus e to the 2 over n to the n is just the same thing as 1 minus e squared, right? When I multiply the exponents there, I just get 2 to the n times n. And so now I'm going to do some cleanup here. So I noticed that, give me a different color. Yeah, Taylor.
What like page are you working in?
5.2.
Like watch it on the computer too, and it's not syncing.
Yeah, it takes time. It doesn't happen instantaneous.
It usually does. I do it every class.
Yeah, sometimes.
An hour.
I'm in 6th hour. I'm in 5.2. So
Yeah, like
it'll come. I know. I can't control how fast it's syncing.
that's okay. Usually it just does it way faster, so I was thinking maybe I was the wrong side.
Oh.
It just showed.
So I hit the sync this page now. So if it was, for whatever reason, if it was taking its time syncing, I told it to like hurry up and do its thing.
Thank you.
Sure. All right. So if I look, those pieces there that I've highlighted in green don't depend on n. So all of those parts I can pull out front of my limit. What I'm left in my limit then, or what's left inside my limit is this, this, and this. Everybody's okay there? Check.
Sorry, what is that 1 minus e squared?
The 1 minus e squared.
Yeah.
When I evaluate this piece, 2 to the n times, yeah, or 2 over n times n is just 2. So that's 1 minus e squared is the numerator. No problem. Okay, so if I try to evaluate this limit now, just doing direct substitution, the numerator is 1, but the denominator is infinity times 0, which is an indeterminate form. So in the denominator, I'm going to have to do a L'Hopital rule to that. Okay? Before I can write it as a L'Hopital rule, though, I have to write it as a fraction. So I'm just going to think about it as 1 minus e to the 2n over 1 over n.
Why do you have to read it as a fraction?
L'Hopital needs to be fraction, has to be a fraction. So if we go back, I guess I don't have it handy. Let me grab this. There we go. Let me grab that real quick so I can show you again. So L'Hopital works if you have an indeterminate form and you have an f of x over a g of x. It has to be written as a fraction. So that's all I'm doing there. So I can do my L'Hopital on it. So out front, we have this. The numerator, when I do the limit, evaluates to 1, because 2 over infinity goes to 0, e to the 0 is 1. The denominator, we have to do our derivative. So the derivative of 1 minus 1 minus e to the 2 over n is going to be negative e to the 2 over n times negative 2 over n squared. So that's just a chain rule. And the denominator is going to be negative 1 over n squared. So n squareds can cancel. And I can now do L'Hopital. Or I'm sorry, I can do direct substitution with the limit. So in the denominator, I have 1, 2, 3 negative signs, so that's a negative. And I have 1, 2 over 1. So just that. So when I multiply this out, then I get e cubed minus e. Again, totally doable by hand, totally outrageously long, took a lot of time. There's a lot of like sneaky algebra that Mr. Gulick had to bend this expression into something we can use a summation formula on. We have to remember a summation formula that maybe we did in Algebra 2 or maybe we didn't, depending on like what class was your Algebra 2 class. So, rough.
So that wasn't necessarily something we were expecting.
Well, here's the thing, Sophia. In one more section, we ditch the infinite or the limit of a sum as our technique for doing integration.
But we still need to know that.
For something easier. I would expect that, like, if I give you the formulas that you need, you could do this. On a problem like this, I would give you, like, you know, the finite geometric series formula. For sure, I would not expect you to have that memorized. And I mean, in all reality, this is not a problem I would put on a test. It's just too time consuming for what it's worth.
And how? Yeah.
Like, I think that this problem, which was like, I think considerably more straightforward, because it was long, but it was really straightforward. You just had to hang on to all your symbols. But the algebra was easy. There's no sneaky things I had to do to like massage the expression to get it to something I could use a summation formula on. It was pretty.
Me when we were doing like the I plus 1 minus 1.
Yeah. Yeah. So like that had so many like sneaky algebra things, and I would not expect you to be able to do, or expect you to do something like that on your own. But as an example, as a homework problem, I think it's fair game on that kind of stuff, but I wouldn't put that on a test. I think it's way too much detail. And to be honest with you, like I sat down and it took me 10 or 15 minutes of like goofing around with this before I could get it to do what I wanted to, because the book didn't give me the answer worked out. It just said, or just had the answer at the end. It didn't have the work to how to do it, because it was a computer algebra system problem. It just wanted you to plug in your calculator and say, okay. I was like, you should be able to do this by hand still. And I was like, yeah, I can. But it took me a minute to do that by hand. It's not something I'd expect you to be able to do by hand. Way too much like non-calculus things that you needed to do to be able to do that. You know what I mean? The previous example, like all the algebra stuff was mostly calculus things, like you use the sum rules over and over and over again.
Yeah, I like that one.
But it was really obvious how to use the sum rules. It wasn't sneaky. That had a lot of calculus in it for the same amount. Like you get the same bang for your, it tells me the same thing, right? In fact, maybe even more. Taylor?
So the part A, the answer that we found was after we found like the x and the x sub I.
Mhm.
That was what we were looking for.
And plugged it into F.
And plugged it. Okay.
Yeah, and we plugged the xi into F. And that's all we did. It just asked us to kind of set this up. And the second part was then to evaluate.
Yeah, so the second part was like.
Yes. Because you had to like do the sum and then you had to do the limit. And neither one of them was easy and direct to do, right? The sum, we had a lot of algebra to get it to a form where we could use the formula. And then the limit had a lot of, we had to do a L'Hopital on it. And a lot of like simplifying or like moving things around or out of the way so that it was even obvious, like this is an indeterminate form that we had to even do L'Hopital on. So it was a rough one all the way around. But I wanted mostly to show you that like even these ones, if you can do it with a computer algebra system, you can do it by hand. And just kind of poopy. Okay. Alternatively, let's take a look at these ones. So again, evaluate the integrals. What could you do? You could do the same thing we've done before, or for these problems, there's another way. So if I look at the f of x here, and I say I square both sides, and then I add the x squared to the other side, what is that? X squared plus y squared is equal to 1. What? Well, this is a specific, what does this graph look like? It's a circle, great. Any more detail? What's the radius? And what's the center? So if I think about this then from like a geometric standpoint, we're looking for the area under the curve from 0 to 1, and I notice that the y has to be positive. So I'm looking for that region. So my area is literally 1/4 pi r squared. Pi over 4, I'm done.
So it's okay if we solve it using the geometry rather than calculus?
Well, again, you're doing the same thing. Like if an integral is an area under the curve, if I can do it geometrically, that's fine. In this case, that's possible. In the previous example was not, because e to the x doesn't create a geometric figure for us that we have an area formula for. But this one did. Sophia?
How do we know that we were looking for that quadrant?
So here, we're integrating from 0 to 1.
Yeah.
And then here, I know that the y coordinate is positive, so it is just quadrant 1 that we're looking for. So the x's from 0 to 1 means either quadrant 1 or 4, or both. But because the y coordinate here is positive, I know that's just quadrant 1. Because the square root can only output a positive number. So if there's no negative sign in front of it, I know that y coordinate for my function has to be a positive. Does that feel okay? Victoria.
Why did you say quadrant 1?
Well, quadrant 1 is here, right? And quadrant 4 is down here.
Oh,
So 0 to 1 covers both of those on the x. But I only want quadrant 1 because I know that the y has to be positive. So that's it. Whoa. That's pretty easy. And it's a good thing it was easy because we don't have a summation formula for a square root function. We don't have one. I mean, there is one, but like it's not one we've talked about ever in another class. It would be brand new, and it'd be, to be quite honest with you, it's a difficult derivation that's beyond the scope of any high school course. So it's a good thing that we just were able to do it like an area problem.
So if we see a square root, we should probably know that it's an area.
I mean, next section, everything gets easier. This problem we can do after next section, we can do it without drawing any pictures, without taking like a half a sheet of paper to do the algebra on it. Life becomes much easier. Yeah, just be patient. And it might be by 5 we can do section 5 we can do this problem. But eventually this problem does not become a difficult problem. Victoria.
when we take like a unit test, like 5
Yes, but it's not necessarily, the skills that I'm going to pick are going to be the ones that are like I'm going to pick skills from 5.2 that are most applicable. And we haven't necessarily gotten to the stuff that I would consider like the stuff that like, oh, going forward, this is the thing you need to have. Now, this definition of an integral will be important, and we can use it still, because these are like approximating a integral using a Riemann sum is a real thing. It's an important technique because not every function is integrable, or even the integration is going to be easy to do. Sometimes it's going to be better just to make an approximation. If you've taken AP Stat, like when you calculate a PDF, that's the area under one of these probability distributions. Those integrals stink. Like they are very, very difficult to do. What you end up doing more often than not is a approximation using a Riemann sum, and that's way nicer. Or even if you do like Bayesian statistic, you'll like do a simulation using like a method called MCMC, like Markov chain Monte Carlo, where you just kind of simulate the function and do like a Riemann sum kind of thing to it to get the probability out of it. And like that stuff is a huge breakthrough because it's heavy computational, like the computer has to do a lot of work to do it, because you usually use a lot of rectangles or like a lot of points to do your approximation or your simulation. But the computer doesn't mind. It's like, it's a second for me. You know, it seems like the same amount of time, whether it's like 10 points or 10,000 points. When your computer does it, it's like just trivial calculation. But it allows us to do things that like before would have been like really time consuming and really tedious pretty nicely. All right, let's look at this other one. So if I look at this, this is just the function here is y equals x minus 1. What is that shape? Well, it's like a line, right?
Oh, that's a line.
Yeah. Yes, the areas are going to be triangles. So if I draw my graph here, so at 0, we're at -1. At 1, we're at 0. At 2, we're at 1. And at 3, we're at 2. So this is my function. So going from 3 to 0, we have these two triangles, right? So the area under the curve, remember, area 1 is going to be a negative area because it's below the x-axis. So we're just going to do the area for triangle 2 minus the area from triangle 1. The area for triangle is 1/2 base times height. What's the base for area or for triangle 2? That's 2. And the height is? So 1/2, 2 squared is just 2. And for triangle 1, the base is? And the height is? So this is 1/2 times 1. So my area is just 1.5. Integral done. So this is a kind of thing where I think doing this on the test geometrically, super reasonable expectation, right? Nothing bad about this. And in fact, I would even say that, like, if I, like, give you some function, that, like, does that or whatever, like, and I ask you to find the integral for this, and I just give you the picture, that's, again, it's doing the same thing. We're just doing it geometrically. We're just calculating the areas.
Would you give us like the area
For like triangles?
like what's this thing on the chart?
Well, I mean, 2 triangles and a rectangle, right?
But it's not like a specific shape.
Who cares? Why not just do it that way?
So many calculations.
But they're formulas you have memorized already. There's no more memorization. Plus, to do this as a trapezoid, you would need to know that length, and maybe that length isn't even super obvious. I don't know. I guess it's not bad.
I guess.
But that's the way I would do it, is just triangles and rectangles, man. You know what I mean? So, like, again, I think that's a super reasonable question to ask you guys, to give you a function, ask you to, like, here's my f of x, find the integral, and all I've given you is the picture of the function, assuming that you can break it up geometrically, right? If it's like a sine function or something, that's unreasonable. Well, kind of unreasonable. We'll see that it actually isn't, depending on what the interval is that we're integrating over, because it'll just be like 0. Right, if you have the same amount above and below, if it's like one period that you're integrating over, you have like this amount above and the amount below is the same, so it'll just be 0. That's reasonable to do. Anyways, okay. So if you remember, when we went back to the very beginning and defined the definite integral, we said that we're going to do f of xi's, where these xi's can be like just any sample point inside that subinterval. So when we do our actual definite integral calculation, we find what the definite integral is actually equal to, we just end up using the right-hand rules because the sample point doesn't matter, so I just pick something to standardize it. If you're going to do an approximation, though, and our function is like always increasing or always decreasing, the right-hand or left-hand rules are always going to be like, each rectangle is going to be an overestimate, or each rectangle will be an underestimate, right? What might be nice is to use like a midpoint rule, where like some of your rectangle overestimates, but then some of your rectangles underestimating it. You might get a better approximation doing it that way. So that's what we're going to look at here in the next spot, is using a midpoint rule to approximate one of these integrals, because, well, it can be a better approximation than either a left hand or a right hand. Or in most cases, it's a better approximation. So, okay, so here's my function. So again, I'm going to start by calculating my delta x. So b minus a over n. So if I'm going from 1 to 2, my next endpoint is going to be 1/5 later. So I have like 1/5 to 6/5, 6/5 to 7/5. Zoom out so I can write these legibly. So these are like my subintervals, right? Everybody's okay with that? Now to calculate, let's find the midpoint for this first, yeah.
And you did 5 intervals, and I did 5.
Correct. Yep. Exactly right. So to calculate the midpoint then inside the first interval, so the notation that in the formula they use a bar, like x1 bar to be the midpoint for interval 1. That's going to just be the first point plus the the endpoints added together divided by 2. To do that calculation quickly, I'm just going to multiply the top and bottom by 5. So that's going to give me 5 plus 6 over 10. So that would be 11/10. Everybody's okay there?
Wait, sorry, what is the line above the X?
That's the notation that the formula up here is using for the midpoint in interval 1 is just the bar. Yeah, it's just the notation. That's our sample point from the first interval is just the midpoint from the first interval. So x1 bar is the midpoint from the first interval. If I do this again in x2, I'll be doing the same thing, right? 6/5 plus 7/5 divided by 2. If I multiply the top and bottom by 5, I get 13/10. What do you notice about between 11/10 and 13/10? They're 1/5 apart, right? They're a delta x apart. So like in general, xi is going to be x1 bar plus I delta x. So it's,
Oh, yeah.
oh, sorry, xi bar. Thank you. Yeah, that means the midpoint,
Oh,
right? So the midpoint from that interval. So on the ith interval, the midpoint should be the midpoint from the first interval plus 6 or plus whatever delta x is. So what's that mean here? The next one is going to be 15/10, 17/10, and then 19/10.
Because you did 11/10 plus I, which is like 3, like the third interval, times delta x.
Yep. Okay, so what's it come out to be at the end? It's base times height plus base times height plus base times height plus base times height plus base times height. How's that? guys. That ain't too bad, right? Could be worse. Darn tootin'. So I'm just going to go type this into my calculator real quick. Notice that Mr. Kulik's being kind of sneaky with how he's typing this in, so he doesn't have to type a billion things in. So each one of them contains a factor of 1/5. So I factor that out. And then they all have a common denominator of 10, so I'm just going to write it as one fraction. So idea at 1.5. Feel okay to you guys? All right. This piece now, these properties that we're going to talk about, properties of definite integrals, these are things that will be useful here and will continue to be useful throughout the rest of the course. So these are things that I would suggest are properties that you need to memorize. Now, they're not really things that, like, I'm not going to ask you to write it out for me, but these are things that, like, are important now, will be important later, will be important forever, as long as we're doing integration. These are things that will be helpful.
Are they like one of those things where we use it so much we'll memorize it? We should memorize it now.
Well, they're also not things that require a bunch of memorization. They're fairly easy ideas. So if I look at this first rule, if I have the integral from b to a of f of x dx, that's the same thing as the negative integral from a to b, f of x dx. So if I switch the limits of integration, it just makes the integral negative. Okay? That's all we're doing. Right? Does that really require to memorize the symbols? I think it's easier just to memorize the idea that if I switch the limits of integration, it just makes a negative sign. Big whoop. But, like, important, we'll use it more often than you'd expect, but it's not really so much like a formula. Okay? The next one is the integral from a to a of f of x dx is 0. If you think about that, if we're going from a to a, what's the width of my rectangles? 0. So the area of the rectangle should be 0. So the integral should be 0. Yeah. Yeah, that's basically what you're talking about. Yep. Okay. And then we have these 4 properties of integrals. So if I look at property 2, the integral of the sum of 2 functions, I can distribute the integral and evaluate each of the functions separately. What does this remind us of? We had the exact same property for sums, right? This is the exact same property that we were seeing for summations. Are we surprised by that? No, because what is an integral really? A sum, right? It's still just a sum. So that should be, that's pretty obvious. Okay. And we can say the same thing about subtraction. These properties that we're talking about right now, Sophia, these are things that we'll use all the time. All the time these get used. Property 3, again, should look familiar. If I have a constant times a function, I can just pull the constant out front of the integral. Well, this formula here is the same as the sum formula, right? We had a sum formula that says we can do the exact same thing, where I can take the constant out front of my summation. Again, since sums and integrals are kind of the same thing, not surprising that we have this property. Where are we going now? The one property that maybe requires a little bit of explanation is this one. So here, our function is like y equals c? What's the graph of y equals c look like? It's a horizontal line. So if I'm going from A to B, I'm just talking about that rectangle, whose base is b minus a, and whose height is c. So, again, would not be difficult to do that integral geometrically, but that formula works as well. Because all you're doing is talking about a rectangle. Again, maybe not obvious looking at it right away, but when you think about it a little bit, oh, that's just going to make a rectangle then. Whoop-de-doo! All right. So let's do example 6 here. It says, use the properties of integrals to evaluate this thing. So the first thing I'm going to do is I'm going to use property 2 to distribute that integral across the sum. Notice that since that dx is applied to the entire thing, when I distribute the integral, I get a dx with each piece. Important that you include the dx with each piece. Now, this first integral, I can just use property 1 on. That's just going to be 4 times b minus a. Everybody's okay there? The second integral, I have this constant. So using property 3, I can pull that constant out front. Is everybody okay there? The unfortunate part is that this, I don't have anything to work on, or to work with this. I have to go back to my definition of a definite integral to do this piece. And then my delta x here is just going to be 1 over n. My xi is going to be 0 plus I delta x. So f of xi is going to be I over n squared.
Can you go back a little after you did the distribution? What did you do, like, right after you distributed the 4x squared?
I used property 1 to evaluate this integral.
Oh, that's how you do that.
And then I used property 3 to pull the 3 out front, to pull the constant out front of the other integral.
Okay.
And now I'm just going back to our definition of a definite integral to deal with this. All right. I noticed that I can then take out a 1 over n cubed. I have an n here and then 2 n's there, so that'll be n cubed. So I have 3 over n cubed as my coefficient. And the sum from 1 to n of I squared. Oops. Sure, what's up?
I know that we have the x squared, but why did you square the I over n?
Because the formula here is going to be,
Oh, and you put it to that.
yeah, this is delta x, and this is f over, or f of xi. So this is like my f of x. So I had to plug xi into, or yeah, xi into f of x. Is that okay? That, the sum from 1 to n of I squared, is something we have a formula for. If you go back and look, it is n times n plus 1 times 2n plus 1 all over 6. Oops, what did I forget here along the way someplace? Yeah, forgot a couple of limits here. This is the beauty of OneNote, right? Makes it easier to go ahead and do stuff like that. Ugh, I just made a mess out of that piece back there. Whatever. Oh, come on now. Okay. And let's just kind of streamline this limiting process here a little bit now. If I look at the numerator, it's going to be a polynomial, right? What's the leading coefficient or the leading term of that polynomial? Well, it's going to be 2n cubed. Everybody agree? And the denominator is 6n cubed. Everybody okay with that? So when I take the limit of that, what am I going to get? I don't care about anything other than those parts. It's going to be leading coefficient over leading coefficient since the degrees are the same. Everybody's okay with that? So that is 4 times 3 times 2 over 6, which is just 5.
What about, did you distribute the 3 in the numerator into the polynomial on the top, or is that?
That's that 3.
Oh, so
I didn't bother to distribute it. I could have if I wanted to.
Okay,
That would have been okay.
you can just leave it out. You can distribute the n cubed. Just because it's the exponent that matters.
Yeah.
Okay.
Just because the exponent that matters.
Okay. So you have 4 plus. Oh, okay. Okay.
Sophia?
Can you briefly do a little recap over of how you got the 2 and 2?
Uh-huh. So if I want the leading term, I'm just going to multiply the leading term of each of those 3. N times 2n is 2n cubed. And the rest of it I don't care about because if I do L'Hopital's rule, those are just going to drop out eventually, right? Yeah, I just looked at the part I cared about because I recognize that this is just like polynomial over polynomial. That's a L'Hopital indeterminate case. I just would L'Hopital it down until I had leading coefficient over leading coefficient.
And then the 6n cubed is from 6 times n cubed.
Yep,
Yeah.
exactly. Victoria.
When you like move it, when you like you see the 3 over n cubed,
Uh-huh.
how did you do that?
So the 3 is just this 3 that I pulled out from way back here.
Yeah.
And the n cubed, if I look, I have n squared.
Yeah.
So n times n squared is n cubed.
How did you get to the? Oh, you just pulled that.
I just pulled it out because it doesn't depend on I.
Okay.
So I can pull it out of the sum, but it still needs to stay inside the limit.
Oh, so that's why the 3 is inside the limit, just because the n cubed is.
The 3 could be outside the limit if you wanted to. That's fine also.
So it could have been like 4 plus 3 over n.
It could be 4 plus 3 limit
1 over n.
1 over n cubed sum yada yada yada. Yeah, you could write it that way also. That's not wrong.
And why didn't you like put it under the 4? Why the 3? Or does it matter?
Why didn't I put it under the 4? What for?
Oh, wait, no, never mind.
Okay. That's okay? Okay. All right. So again, these four properties here of integrals, we will use a ton. Every time we do a definite integral or an indefinite integral, which we'll talk about in another couple of sections, use them all the time. You don't really need to bother memorizing because you're just going to learn them automatically, and there's not much to memorize. It's just like, how can I move my integral symbol around is basically all it's telling me.
Can you spell the fourth property? I wasn't looking at it wrong. It was like,
It's the same as 2. It's just
it's
for
the same as
subtraction.
two subtraction. Okay.
Yeah.
I was like, I thought they were the same. But I was
Yeah. I would have just written them as with a plus or minus, but
like, yeah.
it's not my textbook, so.
Yes.
All right. Another super useful one, it says the integral from a to c of f of x dx plus the integral from c to b of f of x dx is the same as the integral from a to b f of x dx. So once we draw a picture, this becomes like kind of super obvious. So there's our f of x. Let's say this is A, this is C, and this is B. So if we go from, wanted a different color. So if we're going from A to C, you're talking about this area. If you're talking about C to B, we're talking about this area. And then if you're talking about the integral from A to C, you're just talking about this area. So if I add up the blue area and the green area, I should get the light green area, right? That's all this is saying. So the key is that if those bounds are the same, you can just combine them together into one integral. Everybody's okay with that? Which is, I want to point out to you exactly what we did intuitively over here, where we calculated one integral and then a separate integral, where we broke it inside of the limits of integration, right? That this was like the integral from 0 to 1, and this was like the integral from 1 to 3. And we added them together. Oh yeah, that's exactly what I did up here. Super intuitive, right? We did it.
Make sure the little picture you just drew first.
Yeah.
Okay.
So that's like the light green, this is the blue, and this is the dark green. So if I look at example 7, all I'm going to do is use this formula above. So I can say the integral from 0 to 8, f of x dx, plus the integral from 8 to 10, f of x dx, is equal to the integral from 0 to 10 of f of x dx. So I can say that 12 plus whatever is equal to 17. So it's got to be 5. Mr. Kulak, like that's, we did like algebra 1 stuff there. It's given to us in the problem.
Yeah. I see.
So again, the point of it is that if those two numbers are the same, I can rewrite it as a single integral with the lower bound from the first piece and the upper bound from the second piece.
The lower bound of the first piece.
I know the vocab gets tough.
Everything just looks really scary on paper, but it's so easy, like secretly
in graph form.
It looks really scary though with the notation. I think the notation is like the block right now for all of us.
Yeah. Well, I mean, again, I'm trying very hard as we're talking through this to say the words of what's going on more so than like reading the symbols.
Yeah.
Because I want you to look at the symbols and hear the words that I say, because that's what's going to make life easier. So I'm trying very hard to, like, when we're doing this, focus on my words more so than the symbols that I'm writing. Because if you look at the symbols and you hear the words, it's like, oh, only thing that matters are the bounds on this. I'm just looking, if all the functions are the same, then all I'm doing is looking at the bounds. And I'm just wanting to match up the bounds to put them together. It's like the transitive property from geometry. Like if A equals B and B equals C, then A equals C. That's all we're doing here. It's just connecting two things together. All right. I think this is the last set of ideas here in this section. So again, super intuitive. So if our function is always positive over some interval, the integral over that interval also has to be positive. Because if the function is always above the x-axis, when I calculate the area, it has to be a positive area. Really intuitive, right? Okay. Next one. So if one function is bigger than another function over the entire interval, then the integral of that first function has to be bigger than the integral of that second function. If it's always above it, the area of the one on top is going to be more than the area on the one on bottom. Of course, right? Everybody's okay with that? This last one is the one where we're going to draw a picture to kind of really hammer this home. So it says if f of x is bounded between little m and big M, little m we might call the local minimum, and big M we might call the local maximum, where the locality is that interval from A to B. Then m times b minus a is less than or equal to the integral, which is less than or equal to cap m times b minus a. What is this we're recognizing? That was property 1 for integrals. That's the integral from m from a to b. And this would be the integral of cap m from a to b.
What is the notation with the lowercase and the capitals? Just differentiating two different integrals or two different like.
They're just two different numbers.
Oh,
Yeah, where m we usually call the local minimum, and cap m we call the local maximum. Does that feel okay to you guys? So really, what does this look like? Just looks like that property to me, right?
Yes.
Just like two of those properties stuck together. Yeah. So let's draw a picture just to kind of hammer this home, okay? Yes. So this point right here is our local minimum, correct? So we're saying that this area has to be less than the area of our function, or than the value of our integral, the area under the curve. Well, certainly. Of course it does, right? And then this would be our local maximum. So we're saying the area under the curve has to be then less than this rectangle, which of course it does, right? Look at how much overestimate that is. That's all it's saying. If you build a rectangle based on whose height is the lower bound or the local minimum, that has to be smaller than the area under the curve. If we build a rectangle whose height is the local maximum, well, that has to be bigger than the area under the curve. Okay? Now, what's the hitch with using this? Finding those local mins and maxes. Now, the best case scenario is one like this example 8. So our function is y equals e to the negative x squared. So remember that the graph for e to the x looks like this, correct? That's increasing everywhere. What's the graph of e to the negative x look like? What's the graph of e to the negative x squared going to look like? Same thing. The point here is this is decreasing everywhere. So my local minimum, my m, little m, is just going to be f of the first point, or I'm sorry, my local maximum. I'm sorry, my local minimum is going to be the furthest right point I have. So that's going to be the 1. And my local maximum is going to be the furthest left point I have in my interval, which would be 0. So I take those two together, and I can just say e to the negative x is less than or equal to my integral 0 to 1, e to the negative x squared dx less than or equal to 1. There's my approximation, or my estimation. So the best case scenario is you have a function that's always increasing or always decreasing, because then the local min and max are just the endpoints of our function. That's not so bad. Or the endpoints of our interval, I should say. And then e to the negative 1's a number, right? That's like point something or another.
Well, the local min
That's a wrap.
will be the right side.
No. Depends on if the function was increasing or decreasing.
I tell myself every week that I'm not going to win.
What is L dot min? What do you mean by like L dot min?
Local min, local max.
Oh, wait, yeah, we were yeah, that's what I'm saying.
Due dates on stuff. I think 5.1 will just be the first problem set. 5.2 will go into next week's because we haven't had a chance to ask questions about it. And obviously, Sunday at midnight, but really, when's Mr. Kulik going to look at anything? Yeah, Tuesday morning. So, because we don't have school on Monday. So, but my suggestion to you, with the extra day, try to do as much of 5.2 as you can. Right? Don't get behind. Sergio, Sophia. All right. So, quick question for you guys. That closes up the lecture part for section 5.2. Has anybody started the 5.2 homework that has questions that you guys want to ask? We have 10 minutes or so. Nico?
So one of the problems was like use the lower and upper estimate. I don't remember which one, but like so the it was just a line and it crossed the x-axis. So when you're trying to decide whether to use the left or right corner, you just like figure out which rectangle, which like the positive and negative side has more rectangles, and that's the lower or upper estimate. That makes sense.
Are we looking at
It was like number 7.
like number 7? Yes, you can. Okay. So I would just, I mean, from looking at this data table, I'm not sure whether the left-hand limit or the right-hand limit is necessarily going to be, well, I mean, I can, the over-under estimate. But that's all I'm doing, is just doing the left-hand rule and the right-hand rule, and then I'll just see which one's bigger and smaller. I mean, I wouldn't think about it any harder than that. Since it's decreasing, I know the left-hand limits are going to be the overestimates, and the right-hand limits are going to be the underestimates, or the right-hand rectangles, because the right hand is always lower than the left hand since it's decreasing. If I look at the f of x's, they're getting, they're increasing. They're going from small to big. So it'll be the opposite. So the left hands will be the underestimates, because you'll always be lower than the right hand. You know. But that's the idea. Nothing more to it than doing a Riemann sum, though. Just doing rectangles. You're welcome. So just a little preview for 5.3. Fundamental theorem of calculus. What we're doing, we're going to connect this definite integral to the antiderivatives that we did at the end of last chapter.